Alright, time for another DraftScience video presentation. Mostly on kinetic energy, I imagine, but we'll see where it goes after its beginning. So there's a clip. I've been doing some work trying to find different quotes of philosophy and get to the core of mistakes made in the past, I would contend, by physics. And it's just really a bunch of historians, jibber-jabbing about what happened rather than you see the actual evidence that that's what was said or that's what happened or those were the key moments. And they sort of get to decide what are a key moment. I don't know what to analogize it from. It's kind of like they find a matchbook in Elvis's back pocket that has something scrolled on it. And you don't even know whether, it was like he wrote on it. It could have been somebody else. I mean, it's that kind of, you can't be sure what the message really is or how important it really is. So anyway, so Emilie is a key figure in this whole promotion of Leibnizian, the philosophy, physics. And just the way the history turns out is, without a couple of, key figures, things go some other way. So, so I'll just play it because it just illustrates, what I would argue is a real problem in science. And scientists don't see the problem because, they've deluded themselves into thinking they have all the right answers. And they really don't wish to start over at all. And so they just keep riding, the pretty crappy bandwagon. There's clearly some instruments, on the bandwagon that aren't making good sounds. And, they need to edit that. But anyway.
Intellectual life among mathematicians and physicists, which was the question of how you understand what happens when bodies bang together in movement. Think about Newton as being a science about billiard balls, and the question was what happens when the billiard balls bang together. And the Newtonian said that you could understand the force that are moving.
Okay, I'm back. Should be working now.
How was her reputation?
Yes, just to pick up on what Patricia was saying, the story of Newton sitting under the apple tree, we of course owe to Voltaire, who's the first person to publish it. And Voltaire.
So I guess that's something to point out. These people weren't overtly, anti-Newton. It just was, anti-Newton in the sense that they didn't realize that the piece that they were against Newton on was really the whole story. I mean, it really is the core of Newton's physics that they were attacking. So in the sense they're defending the results of Newton and yet attacking the thing that made those results viewable, in my opinion. I mean, that's how fundamental this was.
There is the world's leading Newtonian. What Emilie's reputation depended upon, in part, was her engagement in a controversy which had split intellectual life among mathematicians and physicists.
So the controversy is the mv squared. Okay, so it is the living force controversy. And again, these historians are all talking like it wasn't a real thing, when of course it is a real thing. It was a real thing. And frankly, the wrong side won, and I don't know whether it won for any good reasons. I mean, I have to admit, the people defending Newtonian physics didn't do it very well. I mean, they didn't come up with the obvious statements like, well, what do you think, an 8-pound bowling ball knocks down more pins? I mean, come on. Get real.
Which was the question of how you understand what happens when bodies bang together in movement. We think about Newton as being a science about billiard balls.
Yeah, well, so that's exactly what things are, banging into each other, and it's the only way force can mean something is it has to affect something. So obviously, whether it's at a distance, in the case of gravity, or magnetism, or whether it's because you actually hit it, I would argue nobody really should have seen a huge difference. They should have been able to realize that clearly the force is emanating from something, like the light is emanating from the sun, and you could deduce implications that it's producing the effect, the cause, and then the effect.
And the question was, what happens when the billiard balls bang together? And the Newtonians said that you could understand the force that a moving body had in terms of its mass multiplied by its velocity. Its momentum, as we would now call it.
Right, and it worked. So Descartes and Newton both had that similar basic mechanic. And it really didn't have any major flaws. There wasn't like some glaring place where, oh, this just doesn't work, this just doesn't work. And they went out looking for some excuse to say it doesn't work.
And if you think, for example, of if I were to fire a gun,
so this is, so he's doing the cliche crap, okay, where it seems like, and the scientists should know, wait a minute, you're really not looking at this fairly, so let's make the two circumstances more similar and then you'll get it. So this is like you're saying, okay, this is the kind of argument that if it was made at the time, the wrong side wouldn't have won. So let him finish this one analogy.
Pull the gun into my shoulder, I pull the trigger, the bullet would come out one end, the stock of the gun would go back into my shoulder, and on Newtonian principles, action and reaction are equal and opposite. The force going into my shoulder is identical to the force of the bullet going out.
Well, it doesn't have to be identical, it's equal enough. And yes, and the scientists can appreciate that. A scientist can understand that, oh yeah, well, you're spreading the force over a larger area, and okay, you've given the force a slower velocity because it has much more mass to move. So I could almost draw some of this, and so I will. Yes, that's what I would do. All right, so if we just realize, okay, that we can change things, okay, so let's make the gun a big gun, just because he's sort of describing a big gun. Whole gun, stock, whole pile of crap here, triggers and whatnot. All right, and so you're going to shoot a little bullet, a little tiny bullet, okay? I mean, tiny, grams worth of weight. And here you've got, pounds worth of weight, okay? And so but there will be, this opposite and equal reaction. Now, they're saying it must be mv squared because the bullet does so much more damage, right? The bullet flying at whatever 300 meters per second, and the gun stock. So the gun is so I've pointed out that all we need to do is put a little pointy thing on the end of this gun, right? So if I point the end of the gun like a bullet, so it's a little tiny thing, well, then I've gotten rid of the surface area problem. So now you're going to put the stock of the gun right next to your chest with this pointy thing on it, okay, and fire the bullet. And then the second trick is that, well, this velocity thing matters, okay? So we're going to say that this is going to have the gun's going to have the same momentum as the bullet. This is the dividing point. And you're going to be sending the same joules of energy this way as you are this way. And that would be Newton's theory. And so, like I said, all I have to do is, first I put that point on there and you're going to start getting it. Oh yeah, that's not going to be too healthy, maybe. Maybe that's going to do me some damage. And then if I say, well, let's lighten the gun as much as we can and take away this pound stuff. Let's make it out of like ceramic or something. So now we're starting to get, we're only, instead of being 2,000 times the weight of the bullet or 20,000, let's knock it down to, 10 or 20 or 30 or 40 or 50, well, let's say 100 times heavier. So at least now it's got speed also. So now the recoil is going to be very fast also. So this is going to start moving faster, all right, besides being pointy. Okay, so if I can give it more and more velocity, because I really don't need the heavy mass to do the penetrating, right? Because all I'm really concerned about was this point and how far this little point goes. And I can make the little point go further or go deeper by reducing the mass and increasing the velocity. I should say increasing the velocity and decreasing the mass, because the velocity is the important part. So to understand penetration, so anyway, you get the idea, right? If I make the gun lighter, it's going to move faster. You're not moving the big steel barrel, all this heavy stuff. So you can go much faster here. So that's all we're really talking about. We're talking about what's this little point doing, and that's what the case with the bullet. That's why they pointed bullets. Okay, because it works better. They went from ball to bullet, and because it is more effective. It's just a fact, and so you can sort of get it that okay, now the bullet and this do look a lot more like each other in terms of a weapon. Like if I want to get rid of my mother-in-law, maybe I just turn the gun around, But anyway, so it's not that hard to understand. So if they made those kind of, if they took the arguments and said, look, wait, think about it a little bit. It's the same energy, same amount of energy, and all you're doing is changing how it's like what form the energy's in. So the trick would be, in terms of understanding this whole penetration thing, is to understand, I've sort of just said it's like, some materials, they just don't have time to grab onto something. It takes a minute for them for the friction to have an effect, because they have to sort of chemically bond. They have to sort of bond to the other object. And if you increase the speed of something, then you're decreasing the amount of time it has to interact. And that's where this all becomes really important. You can sort of understand that if it doesn't have time to stick, it doesn't have time to cause a transfer of the energy into the other material. So so the same thing is true for your body and your tissues and all that kind of stuff. The faster you can hit it, it's like breaking the board, with kung fu, the faster you can hit the board, the more you destabilize a one tiny area of the board, and you just split the whole board in half, and then it bends and yields to the energy, and you don't transfer much because you spend very little time in contact. So it's sort of like the contact argument that, if you roll something going 22 miles an hour into something standing still, you can only give this 22 miles an hour. You can't give it more because it starts to leave. And so the quicker something's moving away or off of you or away from you, the less likely you can interact with anything it might interact with too. So all the reflections this thing could cause, the faster this is going, the less likely is it's going to get a reflection back. The less likely this is going to fall into something, and this one's going to push up because this one's pushing in, this one's going to push up. Well, if I'm going fast enough, I miss that contact. So you can understand in lots of different ways how you can avoid having to have friction. So it's like if you push the water down in front of a boat, let's say you had a little thing to just smash the water down, in a way you would just avoid that water. You would avoid contact with the boat, and in a sense fly over the next piece of water, and then you could get over the next piece and the next piece. So you can do things to make it less likely that you're going to encounter as much contact. So when a bullet's going into something, you have to understand it's not spending any time at all interacting with the individual pieces. So the faster it's going, the less contact it's having with the tissues. It's not interacting with a bunch of blood and a bunch of this and a bunch of that. It pushes the stuff out very fast. Everything kind of evacuates, and so its pathway is almost cleared. And the fact is, it's hitting a lot of stuff going forward of it. And you got to understand that stuff it's hitting is actually clearing the path for it. It's like getting rid of the stuff in its way. It's pushing it out of the way. So when the bullet gets to this point here, the stuff here pushed it away already. So it almost gets to go for free there, kind of a thing. And, so the energy keeps going in this direction rather than this direction or this direction or this direction or this direction. So the simplest, I guess, way to think of speed is that it keeps the energy that you're transferring when you're going fast, a large percentage of the energy is going forward, where the slower you're going, the more likely it is that you're sending energy in other directions that will not gain you anything. They're just going to leak into this and be out in this way and this way. where the energy that's still going forward is doing you a favor. It's pushing the pin you hit. Say you hit a pin here and the pin moves into another pin and that moves into another pin. It's doing your work for you. It's still working for you. Your energy is conserved in the sense that it still might as well be your energy because it's doing exactly what you're going to do. Where if you don't, if you aren't able to get the energy to move that way because you're going slower and there's more irregularity in the direction of the energy, then you're not going to be, clearing that road. And you're going to get the pushback of other forces acting because it has more time to act. It's just a time thing. I mean, that's all. The whole thing is just about whether you measure things based on distance or understand that it's the amount of time it's interacting. So it's another way of saying it. So if I'm going really fast, you could argue, and I hit something bigger, okay, obviously I can't give it the same speed I had. It has to go away at some lesser speed, because it's much more massive. So it takes time for the energy to get into something that's bigger than the other object, and that's sort of the time that you're not given. When something's going fast, it ends up just, it ends up, in the case of, I shouldn't go with bigger because that doesn't have a bullet analogy. You're really hitting smaller, lighter things. You're not hitting bigger, heavier things, cells and stuff. That's more about bullets ricocheting or something. So I shouldn't have bothered with that. Well, anyway, that's enough of a point made, I think. So I'll leave it there. I'm just saying that the reason why this survives is this is just like urban legend stuff. It's really, really, really bad physics. So nobody should think about the bullet example and say, oh yes, it's so obvious the bullet has much more energy than the gun has. But that's what the kinetic energy theory says. And it's just not true. All you need to do is reshape the gun into something more bullet-like, and you'll get exactly the same results. You'll have two bullets going, and that's really what the charge was. The charge was pushed. It pushed the explosion, pushed energy in both directions equally, and you have just as much energy in the gun. It's just that the energy is in a different form and is in a lot more mass. And so it's going to distribute its energy slower to the rest of the world. And, but it still had as much energy. If I put all the energy into a bullet, the gun's energy is a lot of energy.
Out of the gun. But when the bullet going out of the gun hits something, it does enormous damage. Well, my shoulder is hardly affected by the stock of the gun going.
All right, so obviously, though, so many more pieces of you are affected by the stock of the gun. So it's putting a minor effect on a lot of things, not a catastrophic effect. And we're really just talking about our measure of what a catastrophe is. So the catastrophe isn't us being hit by energy. We can be hit by a lot of energy if it's spread out. So it's the difference between light bulb and laser beam. Yeah, if I take all the energy and make it into a laser beam, I can bore a hole right through you. But it's still just the 5 watts. It's still just the same amount of energy as, tanning lights or something. Or much less than that even. So it's just in the shape of the energy. So the only thing that makes a difference is the shape of the energy. How many pounds per square inch it's interacting with, and then how fast. There's a bias towards velocity. Most systems cut velocity more slack because there's less time for there to be reflexive interactions. It's less sticky for fast things. It's just a fact, and it has. You recognize that fact. You don't change. Fundamentally your understanding of equal and opposite reaction. You don't deny the fundamental truth that it's the same amount of energy. You can't make up this theory that somewhere the bullet got twice as much or 1,000,000 times more energy from the explosion. It can't, There's no source of that energy. The gun got just as much. And this is in the core of physics. Like I'm saying, this is this old idea. It's just wrong-headed. It's a very immature description of the mechanics. And there it is, still in the core of physics.
Back into it. And the followers of Leibniz said the impact of the bullet has to be understood in terms of what we would now call kinetic energy, which is mass times velocity squared.
Yes, saying it doesn't make it any different than you're just saying that somehow magically the bullet pulled more energy out of the explosion than the gun did. It can't pull more energy out. There's no way it extracts more. It's stuck with its half of the equation, and that's all there is. So, I mean, yeah, I'm just saying. I don't know.
That's to say, as you increase the velocity, you multiply the energy involved. This is what...
So again, you don't do that. You just multiply in some circumstances the potential effect. Velocity has advantage. But see, if I take a spring, springs aren't like other collectors. They really are doing a transfer almost like a kinetic ball. They hit whatever you have in front of the spring and they can push it in and compress the spring. And there isn't a bunch of different contacts with different cells or different things. It's not relying on some other mechanism, and it's collecting the energy in one kind of collector that's very efficient in taking all the energy that might want to go in different directions and making it go in one direction. I mean, the spring is... the spring can move this way or move that way, and it'll always try to regularize, so it's really converting the energy into one direction. Where other impacts, like you drop a pebble into water and the water goes in all directions. It's not a system that collects energy and moves it in one direction.
It takes 4 times as long to stop if you're driving at 60 as if you're driving at 30. And if you...
Okay, so it's just not true. If you equalize the contact with the friction, that is you make the friction just as capable of grabbing, then it won't take you. I mean, if you make the brake pads bigger, and you make the wheels bigger, the tires, and you do all that kind of stuff, you'll get more back to more equal. But again, it's still just a bias to friction. Friction, generally speaking, biases speed. Okay? So, because friction does depend on contact and the amount of time it takes to move pieces of the friction elements. I mean, friction isn't as simple as just little pins, and you just knock down the pins. It's more complicated in the sense that, again, you're knocking them down into surfaces that can push back. And if you're going fast, obviously you're going to avoid all the pushback. You can sort of just get that simple. I mean, there's more than one reason friction has a bias for velocity. And I can just, but I can point out the one that you can sort of understand, that if I'm pushing it this way and something else is going to push back, that's going to take time. And if the object is moving faster than that time, then it never has to interact with the pushback. But if it's going slower, then it pushes something. It does feel the pushback before it gets through, and therefore it has to interact with the thing it already interacted with. It's going to interact with it again and lose more energy to it. So you can understand why certain measuring systems have a bias towards velocity. That is, velocity will penetrate further. Even gravity is telling you this, right? I mean, you know that you can throw the twice as heavy battery, okay, and this one's twice as light, and I could throw them with the same energy, and yes, this one goes 4 times higher. It just means that this one can't collect the friction, the gravitational influence, as quickly because it doesn't have as much of a collector. So it goes through without collecting the opposite force, the gravitational force. But you can know that they have the same energy. I mean, you can know this from your own experience. I mean, you can put a cannonball in one hand and a tennis ball on the other hand and throw them with the same energy, and you'll realize, well, yeah, the cannonball goes 2 inches and the tennis ball goes 10 feet. I mean, it's certainly understandable that there's no way to say the tennis ball has twice as much or 10 times as much energy. That would be stupid, because the force that pushed them. They don't have extra force. They don't have any source of extra energy.
You run into somebody at 60, you do 4 times as much damage as if...
So that's just urban legend, never been measured. You don't do 4 times as much damage, but the fact is that the impact, you will cut through deeper into the other vehicle. You'll create what looks like more damage, but it really isn't more physical heat. It isn't more deformation. It isn't, like, if you really add up all that happened, it's not more. And it's almost, again, you can go back to the hitting a board and breaking it, hitting it with enough energy to crack it versus hitting it, slowly with pressure, and how you crack it in a whole bunch of places. Well, if you really measure all the places where there was cracks created and all the deformation, all the stresses, all the places where the board was stressed and broken, you'll see that the slow pressure broke the board just as much in all kinds of ways. And yes, it looks more dramatic when it breaks into 2 pieces. It looks like it's more, but it isn't more.
If you run into them at 30. So we've got 2 theories about what's happening with moving bodies. One is the theory of momentum, the Newtonian theory, and the other is the theory of kinetic energy, as we would now call it, the live forces, as the Leibnizians called it.
Living force. So and again, and it's clear that both of these can't be right, so there is no compatibility between them. What is the right answer? Okay, they have the same energy, and you're just shaping it differently and putting it into a medium that will collect it differently. And that's it. But you can't change how much energy there is. You're just recognizing that the environment will collect it differently. It collects the energy off slow things different than it collects the energy off fast things. And that's all that gravity is showing you too. Yeah. I was going to say that it's the same amount of time for the tennis ball as it is the cannonball in terms of the time it takes, to stop and then start going back down again, but I'm not sure of that. Probably is, though. So the time they were in the gravity is all how long were they in the gravity? That's telling you how much, how long it takes for the force to stop them. And because the fast thing is going faster, it covers more distance in that same amount of time.
Emilie comes out very strongly on the Leibnizian side, and she gets into an argument with the director of the Academy of Sciences in Paris about this, a man called Mérin, and they publish attacking each other, and Voltaire publishes attacking Emilie on this, just as Emilie had published a negative review of Voltaire's book on Newton. So this is an enormous split in intellectual life, and she is very clearly on the side she's taken. Within a few years, this whole issue is resolved by eventually...
It's just so funny. The whole issue is resolved by science losing its mind entirely. So it's this silly argument in the first place, scientifically. It really should have never happened because there's just no reason, especially then. The competing theory was mv squared. I mean, there wasn't even a half in front of it. So it was a preposterous exaggeration of things' energy. If you took it to the real world and started measuring energy, you'd end up with preposterously disproportional numbers. So this argument should have never taken place, but clearly there's a clear duality, a clear conflict, and it resolves by everybody pretending it's just semantics, when no, this is nowhere even close to just some sort of argument over words. This is clearly an argument over something so fundamental to everything's motion in the universe. It's energy. And again, understand, nobody even attempted, as far as I could tell, to redo Newton's mechanics of the solar system by using mv squared. So none of their proofs was, look how much better the moon goes around the Earth if we use mv squared. So nowhere was this formula really put to any practical use. And the only place it has any use is in places where the answer really doesn't matter.
Everyone agrees that there's right on both sides. There's both momentum and there's kinetic energy.
So everybody agrees, he says. So they agreed to pretend, at some state, but this is just, again, the historians doing physics, which is probably how it all turned into this mush. That somehow the historians said it wasn't a meaningful argument. Yeah, well, you can't, in my opinion, you can't get more core than this. I mean, this is a core disagreement. It's not a minor disagreement. This is a fundamental disagreement. The definition of energy? Oh, come on. This is a serious problem. And it wasn't resolved. There was no good fight. There was no good fight where they make a video, Emilie's people make a video explaining how the gun really does have 476 times less energy. That if I reshape the gun into a tiny mass, if I can put all of the gun's energy into a small mass the size of a bullet, that it won't be just as much of a bullet as the other bullet. If I can keep making it lighter and therefore faster, then I can't turn it right into a bullet. And that's exactly what it would turn into.
And so Emilie's role appears very important in a debate which within a decade has just disappeared out of intellectual life.
She did carry out some very important experiments about
So again, these are the important experiments, and they're just absolute garbage. So instead of the ones they could rely on, the experiments that uses things like springs or use things like magnetism, to bounce things around, to measure how much energy you're getting into an era where, Faraday had already done a lot of this work, but you're in an era of the 1700s where this was already a phenomenon they already knew about. They could take two negative magnets and they could, push one magnet into the other magnet and always get a consistent amount of force back. That magnets were a spring. Really good one.
To work out exactly what was happening. She spread out some soft clay on the floor, and then she dropped balls onto the clay.
That's really not how it took place either. The experiment's done with a block of clay, okay, not spread out clay. So, sorry, historian, not quite right.
From different heights. And as David was saying, how we would explain that now is in terms of kinetic energy and also potential energy. But that concept...
No, nobody smart would do it that way. There's only energy, okay? And that's, potential just has to do with what the environment, internal environment or external environment, may impose upon you. But things don't have potential energy, okay? They just have kinetic energy. The energy of a thing is its motion. Not some potential, like 3 days from now something's going to hit it. You don't say, I have potential energy because someday my atoms will be hit by an asteroid. Like 4,678 years from now, wherever my little atoms, wherever there's a clump of 3 or 4 atoms that were still my atoms, you don't say, oh yeah, well I'll put that in my category of potential energy. No, I don't have that in a category. So even, this is just such a terrible physics conversation. It's just awful. The physics is horrible. And it's just sad that no one else will say it. I don't even know whether other people realize it's horrible. I don't know whether there's other physicists say, oh, gee, they're really hatcheting this to pieces. They're just hacking at facts here. They're just making a horrible mess. You can't get them to say anything. Which is, again, it does surprise me that physics doesn't think it has to do any reasoning. It can just make declarations, and it doesn't have to reason. It doesn't have to explain how it actually works. And so I guess they're so out of that habit that when they see somebody explaining something, instead of saying, oh, they're explaining that badly, they say, why are they explaining? We don't explain, we just declare. So they see the crime as not being declarative. They don't see the crime isn't attempting to explain. The crime isn't explaining badly, which is, again, it surprises me that intelligent people can think that makes sense.
Of energy was a very 19th century one. It didn't exist at all in the 18th century. And what she did was measure the depth of the indentation that the balls made.
She didn't do this, okay, in any other way than somebody else did it, and she replicated it for the purpose of her own verification. So again, this wasn't her contribution to science. She didn't really make any unique contribution to the controversy. She just gleaned other people's arguments and other people's experiments and put that stuff together. So a big difference than, mimicking science and doing science. I'm not trying, the fact is it's unfortunate that, a character I thought of as very interesting just turns out to be a clunker. I mean, I wish this first female to break the, the I can do it too barrier was not a failure because, frankly, she was invested in pretty bad science.
And she showed that what now seems obvious, but didn't at the time.
Oh, it now seems obvious. What should now seem obvious to scientific people is that different substances absorb energy in a different manner, and many substances can have a bias for velocity. The faster something goes, the less likely it's going to be able to interact with the substance in any meaningful frictional way. That's what it's just like the maglev train, right? I mean, it's all about the velocity. Make it go faster, it goes higher. There's a bias built into the system where things that are going fast will be rewarded with no friction, where things going slow will make sparks and grind.
Was that the depth of the indentation was proportional to the height from which she dropped the ball. And
I don't even think we have any real hard scientific verification that actually happens all the time. So I don't even know how good this experiment actually was. Yeah, and how convincing that clay is exactly like gravity in terms of its bias for velocity. It probably depends on how cold the clay is or how warm the clay is. A lot of things probably matter.
And I think that's a very good example of how she had a hypothesis and she tested it using an...
So this is just such a lie, okay? That isn't what happened. She clearly was the Gravenson or whatever his name was, a French scientist. He clearly is the one who did the clay experiments. She didn't have a hypothesis and then prove it. I mean, that's just nonsense.
Experiment, quite a straightforward experiment. And it was one of the important contributions she made because this idea of energy was absolutely crucial in 19...
So it's funny, right? They're talking about this idea of energy is absolutely crucial and be kind of sensible to have the right answer. And they're applauding, we got the wrong answer. We got a really dumb, seems like answer. Rather than doing actual physics where you actually understand the process and why the results are the way they are. And so, and again, this is all in the context that we already invented springs, we already invented magnets, we already invented ways of collecting energy that were reliable and dependable. And so all of this nonsense goes away if you understand those methods. Then then you won't see any of your extra energy. All of the extra energy disappears if you use reliable instruments to collect the energy. That's what the science says. That's the background of this crap. So in spite of what 90% of the experiments would say, we'll go with the 10% of the wacky ones because we want the wacky thing to be true. Because it has something to do with some deity crap or some notion of perfect causes and effects or some other kind of, it's not really religion in the classical sense. It's whatever you call those pseudo-religions. I can't think of the word for it right now. But yeah, fringe religious beliefs.
Century physics. And it was one that Newton himself hadn't formulated.
Patricia mentioned the word...
So that's just nonsense. Newton had formulated. He did make slight arguments in this controversy, just pointing out how momentum works. But again, the bias Newton had, which does come out of this, right? Because the people who were arguing in defense of the Newtonian view had to extend Newton from the space arguments to the contact arguments. Because really most of Newton's physics was in an illustration of the mechanics of the solar system, because that's what he was explaining. So a lot of it isn't about mundane earthly experiments like throwing bowling balls. Don't think they had bowling back then.
Hypothesis. And there's no question that her version of hypothesis, the way in which she talked about it in relation to the natural world and how you understand it and how you experiment to replicate conditions that are part of your explanation, became part of the encyclopedia that Diderot produced in the 1760s, as well as a number of other sections of her lessons in physics. In other words, they just lifted whole...
Yes, so 10, 20 years after she was dead, this happens, right? So she becomes a hero posthumously, because other people, just like she did with Leibniz, she took a failed Leibniz and resurrected him, and then other people took a failed Emilie, you could say, and resurrected that physics.
Descriptions. But hypothesis I wanted to mention in particular because it is really the basis of modern science. You have a hypothesis, you perform experiments, you use mathematical models, and then when you have established enough probability and you can replicate it, you then assume that this is an explanation that comes close to the quotes.
I don't know if that's really the scientific method, but whatever. There's an unanswered question. You propose an answer to it, and you see if the answer actually works. And the point here is there was nothing wrong with momentum. Newton used it, worked very well, and yet they claimed there was some cause to re-answer the question and then come up with an answer that was so preposterously incapable of being correct, in the sense that it was just mv squared, no half in front of it. It was already 100% way off. So again, it was ludicrous rather than just wrong. Now it's just wrong. It's still pretty ludicrous. Well, some of the numbers get ludicrous. The fact that people would argue physics says an 8-pound bowling ball knocks down twice as many pins. That's still pretty ludicrous. That, if I make a half-sized wrecking ball, okay, and move it twice as fast, I gain twice as much energy. I can knock down twice as many buildings in the same amount of time. When absolutely no evidence that could possibly be true, because no company has ever seen that energy being realizable. It'd be so much nicer to have smaller cranes and not have to have heavy instruments, can drag all these heavy things to the thing. You could just drag a bunch of little light ones and have them do the job. But the light ones don't work better.
Truth.
David, we know that Emilie worked extremely hard on her ideas. I think I've already mentioned she only took 3 or 4 hours of sleep a night. Was there any signs that she was frustrated by the obstacles?
So I guess that's verified by the fact that in her own descriptions of her own habits, she would force herself to do this. So it wasn't like it was something she did naturally, that she would actually keep ice water on the desk to force herself to stay awake, that kind of stuff. So this was more of a an idea of not losing time. Time was valuable to her, and that does make her very interesting as a character, is the fact that she wanted to make the most of her time. And it's kind of tragic that she was killed having a stupid baby. That just, that the uterus did her in.
She faced among this masculine hegemony.
It's very interesting. In her essay on happiness that she worked on for quite a long time towards the end of her life, she says she's, again...
At the end of her life, right towards the end of her life at 43. Obviously, it wasn't her intent to have the end of her life. Now, she, while she was pregnant, she did sort of have a premonition about dying, so she did do a lot of finishing up and cleaning up of her philosophical papers and whatnot. So they were probably all kind of just, rushed to some form of completion out of a sense of desperation, because she kind of, apparently, she might have learned from, she had 3 kids previously, that maybe pregnancy doesn't agree with her, because she was pretty afraid that this pregnancy was going to kill her.
It's ambition, but ambition, I think she means trying to get a better job, as it were, which is something that she couldn't possibly hope to have. She had ambitions for her husband. And
well, whatever. I don't think that was really something. I mean, she knew she could write papers and submit them as a fake man, and that would be circulated among other people. So she knew she had reason to think she could challenge authority. And she learned it from Voltaire. Voltaire was he was an expert at being a meme controller.
For her son. But what she's in favor of is the pursuit of glory. And by glory, she means reputation, fame. She is very determined to establish herself as a major intellectual figure. And at the end of her life, when she's pregnant and she believes that there's a real prospect that she may die in pregnancy, in birth, which is what happens, she packs up her Newton manuscript and her essay on happiness.
So I hadn't heard this before. So, yes, that's the same way I understand it. So he's just repeating what I understand to be the fact that... she had to finish up.
And she sends them off to the Royal Library so that they will be held there. She's afraid that when she dies, her husband will just throw all her papers out. Well, he's not interested in this sort of thing. They'll be held there, and they can then be preserved for posterity. So there's absolutely no question that she sees herself as somebody who has the...
Okay, so I won't keep playing all this jibber-jabber. It doesn't have much to do with the physics. So we got to the main controversy. They just kind of sloughed over it. Frankly, that's really the extent of her contribution, and it's a negative contribution. She didn't really contribute much on other subjects. She did study fire and different things, but she didn't say anything terribly innovative or critically new. So, and then she did some translating of Newton and different things, but there's lots of translators in history. It's not like, okay, she did a good job of translating. That's not exactly doing science, but whatever. So, it is what it is. So we'll just call that a video. I guess there's no point in going any further. But this isn't this kind of drama and silly bullshit and personal life stuff and blah blah blah. All of this little crap doesn't have much to do with what you would call good science. I mean, good science should just be about the hypothesis and the evidence. And clearly that process took place in an atmosphere that really didn't care about the evidence. It just cared about the standing of the contributors, and there really wasn't a good jury. The jury was ambiguous. Who made the decisions is, who knows? You can almost argue it's like that now, right? They invented this idea of dark matter, and what did it grow out of? Well, one physicist, then another guy says, yeah, I like that. And then another guy says, oh, I like it too. And then another guy says, I like it too. And it's just some sort of, Me Too movement rather than any good science about actually having a debate about whether there's any reason to believe this at all, that I might as well say gremlins did it. If I'm going to invent a brand new form of matter, why don't I just invent a brand new form of boogeyman? You know. Anyway. Alright, so enough of a video, I suppose. No comments of interest, no anything at all. Okay, so it is funny that people they know the kinetic energy formula is right, and yet I can't see anybody defending it against any of the arguments I've made opposing it. So they haven't in any way pointed out, really, they haven't done anything really serious about explaining why I've misunderstood the evidence, and that the real evidence says it does exist, that there is some reason to believe, some necessity to believe that energy is proportional to velocity, essentially, and that mass is very unimportant. You know, where momentum answers all the questions. Just follow the movement, and that's all there is. One thing causes another thing to move, causes another thing to move, and it just keeps moving. And the only thing that stops it from moving is being trapped somewhere. Yeah, going back and forth. Anyway, so enough of a video. Till the next time and such. Who knows? I mean, there's no conversation to be had. There's no. I mean, it's harder to. It's hard to make an argument in science now than it was back at her time. I mean, that's another bizarre irony, is that there's a real ceiling against conversation relevant to science. You go on a message board and they don't want to hear it. They just don't want to have to deal with any critiques of their Bible. And all they'll do is insult you instead. So if you propose something, they'll tear it to pieces, but they will not allow themselves to be critiqued or exposed. And it's really bad science by really bad scientists. The intellectuals really are pretty much just religious assholes. So, till the next time and such, and so forth and whatnot. All quite depressing. And such. Depressing and such.